Only 5%. That's how much of the universe is made up of baryonic matter, protons, neutrons, and electrons. The tangible stuff. The things that we can touch, measure, burn, break down, or build with. It includes stars, interstellar gas, planets, even us. All of it combined to make up less than 20th of everything that exists. So where's the rest? The short answer is, we don't know. But we're trying. The longer answer began almost a century ago when Swiss-American astrophysicist Fritz Zwicky observed the Coma cluster in 1933, calculated the mass of the galaxies using the viral theorem. He found the galaxies were orbiting the cluster center so fast that they should have torn free, unless there was hidden mass exerting gravitational pull. He called it Dunkel Materie, or dark matter. His claim, it was dismissed, but it didn't go away. In the 1970s, American astronomer Vera Rubin and Ken Ford studied the rotation curves of spiral galaxies like Andromeda. Using spectroscopic data, they measured the Doppler shifts of stars. Rubin discovered something profound. Stars at the outer edges were moving just as quickly as those closer to the core. That violates Newtonian mechanics, unless there's an invisible mass halo, much larger than the luminous matter. By the early 2000s, dark matter had gone from fringe theory to mainstream cosmology. It now accounts for roughly 27% of the universe's total mass energy density. But that's not the most disturbing part. In 1998, two independent research teams, the High Z Supernova Search Team and the Supernova Cosmology Project, used Type 1a supernovae as standard candles to calculate cosmic distances. They expected the expansion of the universe to be slowing down, but instead they found acceleration. Something was working against gravity, something that they called dark energy. Today, the lambda cold dark matter model, the standard cosmological model, tells us that the universe consists of 5% ordinary matter, 27% dark matter, and 68% dark energy. So, what is dark matter? It doesn't emit, absorb, or reflect electromagnetic radiation. It doesn't interact with the strong or weak nuclear forces. It's not antimatter, and it's not black holes. It's invisible, but its gravitational fingerprint is unmistakable. The leading candidates are theoretical particles, WIMPs, weakly interacting massive particles, axions, ultralight particles proposed in quantum chromodynamics, and sterile neutrinos, a hypothetical version of neutrinos that don't interact via the weak force. None have been conclusively observed. So what about dark energy? Well, it's not a particle. It's a property. Maybe a cosmological constant, a built-in feature of space-time itself, as Einstein proposed. Or maybe it's a dynamic field, something called quintessence, that evolves over time. It could even be a sign that gravity behaves differently over vast scales, suggesting that general relativity is incomplete. We've built billion-dollar machines to search for answers. The Large Hadron Collider at CERN, it has tried to detect supersymmetric partners. The Lux Zeppelin detector in South Dakota sits 1.5 kilometers or 0.93 miles underground, waiting for dark matter to interact with xenon. NASA's Roman Space Telescope, launching soon, will measure the effects of dark energy through weak gravitational lensing and baryon acoustic oscillations. And yet, despite all this, we're still in the dark. The effects are clear. Dark matter bends light from distant galaxies, an effect called gravitational lensing. It holds galaxies together. Dark energy drives them apart. But what they are fundamentally, we don't know. This is more than a physics problem. It's a reckoning. Because if we can't account for 95% of the universe, then everything we thought we understood about cosmology, entropy, even time's arrow, it might all just be a partial truth. It challenges the scientific method itself, forcing us to build instruments to detect something that we don't even know how to define. Some physicists now believe that dark energy may one day push the fabric of the cosmos to a big rip, where the expansion becomes so extreme that galaxies, stars, planets, even atomic structures are pulled apart. Others suggest a gentler big freeze, a cosmic heat death with no more usable energy, just cold, dark silence. Still others propose something cyclical, a universe that expands and contracts in perpetuity. None of this is confirmed, though. And yet, we continue to search, because discovery doesn't start with knowledge. It begins with wonder. The mystery of dark matter and dark energy, it doesn't just expose our limits. It defines them. And in that darkness, in that absence of knowing, we find the reason to keep looking up. These are Interesting Things with JC.